Imagine standing on Mars billions of years ago. The sky is hazy, tinged with a soft orange hue. Rivers snake across the land, feeding into vast lakes and perhaps even a northern ocean. Rain falls gently, carving valleys into the red soil. In this ancient world, conditions might have been just right for life to begin. This vision isn't mere fantasy. Scientific evidence suggests that early Mars was warmer and wetter than it is today. Features resembling dried-up riverbeds and lake basins hint at a time when liquid water was abundant. For instance, the Gale crater explored by NASA's Curiosity rover shows signs of an ancient lake that could have supported microbial life. The presence of water is crucial because on Earth, where there's water, there's life. Mars' early environment, with its rivers and lakes, might have provided the necessary conditions for life to emerge. If life did begin on Mars, it would have profound implications for our understanding of life's origins. One compelling piece of evidence is the discovery of certain minerals that form in the presence of water. These minerals suggest that Mars had a stable, long-lasting presence of liquid water. Moreover, organic molecules, which are the building blocks of life, have been found in Martian rocks. The idea that life might have started on Mars before Earth challenges our understanding of life's uniqueness. If life began independently on both planets, it suggests that life might be common in the universe. Alternatively, if life started on Mars and was transferred to Earth via meteorites, it would mean our own origins are Martian. This possibility raises questions about the nature of life and its resilience. Could life have survived the harsh journey from Mars to Earth? Some scientists believe that microbial life could endure the conditions of space travel, making this scenario plausible. Understanding whether life existed on Mars also informs our search for life elsewhere. If life arose on Mars, it increases the likelihood that life exists on other planets with similar conditions. It would suggest that life is not a rare occurrence but a common outcome given the right environment. Imagine a quiet night. You look up at the night sky. Stars twinkle above. The moon casts a gentle glow. It's peaceful, familiar. But what if, among those stars, there's life? Not just planets or rocks, but living beings, creatures with thoughts, feelings. Now imagine we find them. This discovery would shake our world, not just in science, but in every part of our lives. Science would be the first to feel the tremble. For years we've searched, telescopes scanning the skies, rovers exploring Mars, scientists analyzing data, always hoping, always wondering, are we alone? If we find life elsewhere, it's a resounding no. This would mean life isn't unique to Earth. It can arise in other places. Perhaps it's common. This changes our understanding of biology, of evolution, of the very essence of life. Religion would also face profound questions. Many faiths teach that humans are special, created with purpose, in the image of a divine being. If life exists elsewhere, what does that mean? Are they also created with purpose? Do they have souls? Some religious leaders have pondered this. The Vatican's astronomer Guy Consolmagno once said that finding aliens wouldn't contradict faith. Instead, it would expand our understanding of God's creation, but not all would agree. Some might struggle, rewriting doctrines, reinterpreting scriptures, seeking answers to questions never before asked. Philosophy would not remain untouched. For centuries, we've debated our place in the universe. Are we the center, the pinnacle of existence? Discovering extraterrestrial life would challenge these notions. It would force us to reconsider our significance. Are we just one of many? What does it mean to be human in a universe teeming with life? These questions would spark debates in classrooms, in cafes, in homes, everywhere. Long ago, we looked up at the sky and saw Mars. It shone red like a glowing ember. To ancient eyes, it was mysterious and powerful. The Greeks named it Ares, the god of war. The Romans called it Mars. Its color stirred the imagination. It was the winter of 1609. The air in Padua, Italy was cold and still. A man stood quietly on a rooftop holding a strange tube-shaped object. His name was Galileo Galilei. He was a teacher of mathematics and a curious thinker. That night, his life, and our view of the universe, was about to change. Galileo was not the first person to look up at Mars. People had watched the red planet for thousands of years. The Babylonians, Egyptians, Greeks, and Romans all studied it. They saw it as a bright red star that moved across the sky in strange patterns. Mars would wander, sometimes speeding up, slowing down, or even going backward. This motion confused people, but they watched it with their eyes alone. Galileo, however, had something new. He had a telescope. The telescope had just been invented in the Netherlands a year before, in 1608. It was first used by sailors and soldiers to see things far away on land or sea. But Galileo had a different idea. What if he pointed it at the sky? He built his own telescope, improving it many times. His best version could magnify objects 20 to 30 times. That might not sound like much today, but back then it was revolutionary. It was like suddenly being able to see with the eyes of an eagle. One night, Galileo turned his telescope to a glowing red dot in the sky. That red dot was Mars. It looked like a tiny star to the naked eye, but through the telescope it became something more. It was no longer just a dot, it was a disk, a round shape. This was a major discovery. Stars always looked like points, even through a telescope, but Mars had a shape. That meant it was something closer and different, something like Earth. Galileo did not see details on the surface of Mars. His telescope was too weak for that. He couldn't see the polar ice caps or the famous canals that people would later imagine. But what he did see was enough to spark a revolution. Mars was a world. Later in 1659, Christian Huygens observed a dark spot on Mars. He watched it move and realized Mars rotates much like Earth. He even estimated that a Martian day was about 24 hours, close to our own. As telescopes improved, astronomers saw more. In 1877, Giovanni Schiaparelli, an Italian astronomer, mapped Mars during a close approach. He noted lines crisscrossing the surface and called them canali, meaning channels. But in English, canali was translated as canals, suggesting artificial structures. This sparked the idea that intelligent beings might have built them. Percival Lowell, an American astronomer, was captivated by this notion. In the 1890s, he built an observatory in Arizona to study Mars. He believed the canals were real and mapped them extensively. Lowell thought they were built by Martians to transport water from the polar caps to arid regions. He published books and gave lectures, sharing his belief in a dying Martian civilization trying to survive. The public was fascinated. Newspapers and magazines featured stories about Mars and its supposed inhabitants. Science fiction writers were inspired. In 1898, H.G. Wells published The War of the Worlds, imagining an invasion by Martians seeking a new home. In 1911, Edgar Rice Burroughs wrote A Princess of Mars, depicting a planet filled with exotic creatures and cultures. These stories captured the imagination and brought Mars to life in people's minds. However, not everyone agreed with Lowell's ideas. Some astronomers couldn't see the canals he described. They suggested the lines were optical illusions, tricks of the eye and telescope. As technology advanced, clearer images of Mars showed a barren landscape, lacking the straight lines Lowell had drawn. By the mid-20th century, most scientists concluded that the canals were not real. Despite this, the idea of life on Mars persisted. The notion that another planet might harbor life was compelling. It challenged our understanding of the universe and our place in it. The early observations, though flawed, opened the door to exploration and curiosity. They led to questions that scientists continue to pursue. Is there life beyond Earth? Could Mars have once supported life? The story of Mars is a story of human curiosity and the desire to understand our universe. It's a tale of observation, imagination, and the pursuit of truth. As we look back, we gain insight into how our perceptions have evolved. And as we look forward, we continue to seek answers to the mysteries that Mars presents. Mars today is a cold, dry world with a thin atmosphere, yet recent discoveries suggest it once had conditions that could have supported life. The planet's surface is barren, with temperatures often dropping below -220 degrees Fahrenheit. Its atmosphere is about 100 times thinner than Earth's and lacks a protective magnetic field, exposing the surface to harmful radiation. Mars is a cold, dry world today. Its sky is dusty and thin, and its surface is covered with rocks, sand, and rust-red soil. The temperatures can drop far below freezing. There is no liquid water that we can see on the surface, only frozen ice at the poles and hidden under the ground. Mars looks like a place where life could never survive. But things were not always this way. Thanks to many years of research, scientists now believe that Mars was once much wetter. Long ago, the planet may have had lakes, rivers, and even a thicker atmosphere. One of the strongest pieces of evidence comes from a very special robot, NASA's Curiosity rover. Curiosity landed on Mars in 2012 in a place called Gale Crater. This crater is a huge bowl-shaped hole about 154 kilometers wide, formed by a giant impact long ago. In the middle of this crater stands a tall mountain called Mount Sharp. Scientists chose Gale Crater as the rover's landing site because they believed it might hold clues about water and possibly ancient life. They were right. As Curiosity drove across the crater floor, it found rocks that looked very familiar. Some of them had layers, like the kind we see in riverbeds and lake bottoms here on Earth. Others had small pebbles and smooth grains shaped by flowing water. These rocks told a story, one written in stone over billions of years. The biggest discovery was clear signs of ancient lakes and streams. The rover found places where water once pooled into a lake, deep enough to last for thousands or even millions of years. It also saw signs that water flowed downhill, carving small channels into the land. This flowing water carried mud and sand, which settled and became layered rock over time. Curiosity even found chemical clues. Some of the rocks contained clay minerals. These minerals usually form when water interacts with volcanic rock. On Earth, clays are common in riverbanks, lakes, and oceans. Their presence on Mars is a strong sign that water was once there, and that it stayed for a long time. All of this points to one surprising truth. Mars had a very different past. Long ago, it may have had a climate that could support life. Maybe not the kind of life we know, like plants or animals, but perhaps simple microbes. So what changed? Why did Mars go from wet to dry? That part of the story is still being studied. Scientists believe Mars lost much of its atmosphere over time. Without a thick atmosphere to hold in heat and pressure, water couldn't stay liquid. It either froze or escaped into space. Still, the traces of water remain, etched into the rocks, locked in the soil, and remembered by rovers like Curiosity. Mars may be dry now, but long ago, it flowed with water. And where there is water, there is always the chance that life once existed. Additionally, radar data from the European Space Agency's Mars Express orbiter detected a potential subglacial lake beneath the South Polar ice cap, suggesting that liquid water may still exist underground. Methane detections have also intrigued scientists. Curiosity observed spikes in methane levels, which on Earth can be produced by microbial life or geological processes. While the source of Martian methane remains uncertain, its presence raises the possibility of biological activity. Furthermore, the Perseverance Rover has identified organic molecules in Jezero Crater, a site believed to have once hosted a lake. These molecules are the building blocks of life, although they can also form through non-biological processes. These findings suggest that Mars had a more hospitable environment in its past. The presence of water, organic compounds, and methane indicates that the planet may have supported microbial life. As exploration continues, scientists hope to uncover more about Mars's history and its potential to harbor life. In 1976, NASA's Viking 1 and Viking 2 missions became the first to land safely on Mars and conduct experiments directly on its surface. Each lander carried instruments designed to detect signs of microbial life. One experiment, known as the labeled release test, yielded results that some interpreted as positive for microbial activity. However, the scientific community remains divided, with many attributing the findings to non-biological chemical reactions. In February 2021, another remarkable robot touched down on the surface of Mars. Its name is Perseverance. Built by NASA, this six-wheeled rover is one of the most advanced machines ever sent to another planet. Its landing site was Jezero Crater. Today, it looks barren and lifeless. But billions of years ago, things were very different. Scientists chose Jezero Crater because of what it used to be, a lake. Long ago, water flowed into this crater through a winding river, forming a delta, a fan-shaped area where sediments, minerals, and maybe even signs of life settled and collected. That ancient lake may have lasted for millions of years, creating the perfect conditions for simple life to exist. If Mars ever hosted life, Jezero is one of the best places to look. That's exactly what Perseverance is doing. Unlike earlier Mars missions that only observed and analyzed the surface, Perseverance is also preparing for the future. One of its biggest goals is to collect rock and soil samples, carefully drill them, seal them in tubes, and store them for a future mission that will bring them back to Earth. Since its landing, Perseverance has been exploring the Delta area, searching for rocks that could reveal what Mars was like billions of years ago. Some of the rocks it has studied are rich in minerals that form in the presence of water. Others contain organic molecules, carbon-based compounds that are the building blocks of life as we know it. Even more exciting, some rocks have chemical fingerprints that suggest they may have formed with help from microbes, tiny, single-celled organisms. On Earth, similar rocks form when microorganisms live in water and slowly leave behind mineral patterns as they grow and die. Finding such features on Mars is a big clue. It hints that life might once have existed there, even if only in microscopic form. These chemical patterns can also form through non-living processes, such as volcanic activity or chemical weathering. That's why scientists need more data. The samples Perseverance is collecting will eventually be studied in world-class laboratories on Earth, where powerful instruments can search for signs of ancient biology in ways that no rover could do alone. So far, Perseverance has drilled into several rocks and sealed over a dozen sample tubes. It's also testing a tiny helicopter named Ingenuity, which helps scout the terrain from above. Together, these tools are helping unlock the secrets of Mars layer by layer. High above the surface of Mars, a quiet explorer has been circling the planet for nearly 2 decades. This spacecraft is the Mars Reconnaissance Orbiter, or MRO for short. Launched by NASA in 2005, MRO was designed to do something very important: observe the planet in detail from orbit. Unlike the rovers that drive across the ground, MRO never touches the surface. Instead, it flies high above, capturing breathtaking images and scanning the landscape with powerful scientific instruments. From its orbit, MRO has become one of the most important eyes in the sky for Martian science. What makes MRO so special is its incredible camera. Known as HIRIS, the High-Resolution Imaging Science Experiment, it can take pictures so sharp that scientists can see objects as small as a dinner table. These images have shown us Mars in stunning detail, revealing cliffs, dunes, craters, and ancient riverbeds. With every orbit, MRO helps build the most detailed map of Mars we've ever had. But MRO doesn't just take pretty pictures. It also looks for signs of water, and in doing so, it has helped change how we understand Mars. One of MRO's most important discoveries came from a tool called the CRISM spectrometer. This instrument looks at the planet's surface and breaks down the light reflected from minerals. Some of those minerals only form in the presence of water. For example, clays and hydrated salts show up when rocks are soaked or altered by liquid water. Despite these missions' successes, confirming the existence of life on Mars remains challenging. The harsh surface conditions, including high radiation levels and a thin atmosphere, make it difficult for life as we know it to survive. Additionally, distinguishing between biological and non-biological sources of organic molecules and other potential biosignatures is complex. Until samples are returned to Earth for detailed analysis, the question of life on Mars remains open. Mars has always been a mystery. We have sent many missions to explore it. We have found clues that suggest it might have once supported life, but we have not found definitive proof. Some scientists believe that the lack of proof means there is no life on Mars. Others think we might not be looking in the right way. Perhaps we are asking the wrong questions. In 1976, NASA's Viking landers conducted experiments to detect life. One experiment showed positive results, but others did not. Scientists later discovered that chemicals in the Martian soil could have affected the results. This made it difficult to draw clear conclusions. More recent missions, like the Curiosity and Perseverance rovers, have found organic molecules and signs of ancient water. These findings suggest that Mars might have been habitable in the past, but they do not confirm the presence of life. One challenge is that life on Mars, if it exists, might not resemble life on Earth. It could be based on different chemistry. Our instruments are designed to detect life as we know it. If Martian life is different, we might not recognize it. Another issue is that signs of life might be hidden underground. Mars's surface conditions are harsh, but below the surface there might be more stable environments. Drilling into the Martian subsurface is difficult, but it might be necessary to find evidence of life. Some scientists propose that we need to broaden our search. Instead of looking for specific signs of life, we should look for anomalies, things that cannot be explained by known geological processes. This approach might help us identify unfamiliar forms of life. The lack of proof does not necessarily mean there is no life on Mars. It might mean that we need to change our approach. We need to ask new questions and develop new methods. Only then can we hope to uncover the secrets that Mars holds. Recent studies suggest that Mars once harbored vast oceans, rivers, and a thicker atmosphere, painting a picture of a world that may have been hospitable to life. Evidence from various missions and research supports this view. For instance, NASA's Curiosity rover discovered significant amounts of the iron carbonate mineral siderite in rock samples from Gale Crater, indicating that Mars once had a warm and wet climate capable of supporting bodies of liquid water and potentially life. This mineral forms in environments rich in carbon dioxide, suggesting that Mars previously had a thick atmosphere that created greenhouse warming. Further supporting this, a study by Chinese and American researchers using data from China's Zhurong Mars rover suggests that Mars once had beaches as beautiful as those on Earth, potentially fostering life. Mars had extensive water bodies 3 billion years ago, evident from its ocean basins, riverbeds, and deltas. Then, Mars lost its magnetic field, and solar wind eroded its atmosphere, evaporating much of the water. Additionally, new observations indicate that early in its history, Mars had an open ocean with tides and wind-driven waves that deposited sediment on the beach. On Earth, ocean tides and winds carry sediment toward the shoreline, where the sediment settles out to form a beach deposit with a characteristic dipping angle. Similar features have been observed on Mars, suggesting the presence of ancient beaches. These findings collectively paint a picture of ancient Mars as a planet with a dynamic climate and abundant liquid water, conditions that could have supported life. Understanding this past environment is crucial as we continue to explore Mars and search for signs of past or present life. Billions of years ago, Mars might have been a world not unlike Earth. It had flowing rivers, vast oceans, and a thick atmosphere. The planet's surface was warm and wet, creating conditions that could have supported life. NASA's Curiosity rover discovered ancient riverbeds and minerals that form in water, indicating that water once flowed on Mars. The Chinese Zhurong rover detected buried evidence of ancient sandy beaches, suggesting the presence of a large ocean about 3.5 to 4 billion years ago. These findings suggest that Mars had a climate similar to early Earth's, with a stable ocean and a thicker atmosphere. This raises the question, did life have a head start on Mars? Some scientists believe that life may have emerged on Mars before Earth. Mars cooled faster than Earth, providing a longer window for life to develop. If life did arise on Mars, it might have been similar to early Earth microbes. However, Mars underwent significant changes. Its atmosphere thinned, and the planet became colder and drier. This transformation could have forced any existing life to retreat underground or become extinct. Despite these changes, some scientists believe that microbial life could still exist beneath the Martian surface. Subsurface environments may provide the necessary conditions for life to survive. Future missions aim to explore these regions in search of signs of life. The possibility that life once existed on Mars, or still does, continues to captivate scientists and the public alike. As we continue to explore the Red Planet, we may uncover more clues about its past and the potential for life beyond Earth. One significant concern is the risk of contamination. Despite rigorous sterilization protocols, Earth microbes can hitch a ride on spacecraft and potentially survive the journey to Mars. Studies have shown that certain hardy microorganisms, like Deinococcus radiodurans, can withstand extreme conditions, including high levels of radiation and desiccation. This resilience raises the possibility that Earth microbes could survive on Mars, at least for a time. If these microbes were to be detected by instruments searching for Martian life, it could lead to false positives, confusing Earth-originating life with indigenous Martian organisms. This scenario underscores the importance of planetary protection measures and the need for careful interpretation of data collected from Mars missions. Beyond biological concerns, political and funding challenges also impede deep space exploration. Space missions are expensive and require long-term commitment, which can be difficult to maintain amid shifting political priorities. For instance, proposed budget cuts to NASA have raised concerns about the agency's ability to carry out its scientific missions. Former NASA Administrator Bill Nelson criticized such cuts, likening them to attacking the agency with a chainsaw and a meat axe, warning that they could severely harm NASA's core scientific research and technological development. These funding uncertainties can delay or derail missions, limiting our ability to explore Mars and other celestial bodies. Its reddish hue and proximity to Earth make it a prime candidate in the search for extraterrestrial life. Over the years, scientists have developed various theories about the possibility of life on Mars. These theories range from optimistic to skeptical, with some proposing a middle ground. Optimists believe that microbial life may still exist beneath the Martian surface. They argue that, while the surface is harsh and inhospitable, the subsurface could provide a more stable environment. Studies suggest that underground regions may have the necessary conditions to support life, such as the presence of water and protection from harmful radiation. For instance, research indicates that rocks in the Martian crust could produce chemical energy similar to that which supports microbial life deep beneath Earth's surface. This energy could potentially sustain life forms in the Martian subsurface. Additionally, evidence of vast underground reservoirs of liquid water on Mars further supports the possibility of life existing below the surface. On the other hand, skeptics argue that Mars has always been lifeless. They point to the planet's small size and inability to retain a thick atmosphere as factors that would have prevented the development of life. According to this view, Mars was born with a fatal flaw that doomed it to become a barren, lifeless place. The lack of a substantial atmosphere would have led to the loss of water and exposure to harmful radiation, making the planet inhospitable from the beginning. Between these two extremes lies a middle ground perspective. Some scientists propose that life might have started on Mars but eventually died off due to environmental changes. They suggest that ancient Martian life may have initially prospered, but its own biological activity could have altered the atmosphere, leading to a global cooling event that rendered the surface uninhabitable. This theory posits that microbes could have driven climate change by consuming hydrogen and releasing methane, ultimately causing their own extinction. These differing viewpoints highlight the complexity of the search for life on Mars. While some remain hopeful about the possibility of existing life beneath the surface, others caution that the planet may have never supported life at all. The middle ground theory offers a nuanced perspective, acknowledging the potential for past life that could not withstand the planet's changing conditions. As exploration continues, future missions may provide more definitive answers to this enduring question. In recent years, the exploration of Mars has expanded beyond traditional space agencies. Universities, private companies, and independent researchers are now contributing to our understanding of the red planet. For instance, the Mars Society has established the Mars Desert Research Station in Utah, simulating Martian conditions to prepare for future missions. Similarly, the University Rover Challenge encourages students worldwide to design and build rovers for Mars-like terrains. Private enterprises are also making significant strides. Organizations like Mars Discovery District in Canada support startups focusing on space technology and innovation. Collaborations between companies and academic institutions, such as the partnership between Mars Incorporated and UC Davis, aim to advance research in areas relevant to space exploration. Beyond mainstream science, some researchers and enthusiasts explore unconventional theories about Mars. They examine satellite images and geological formations, proposing hypotheses about the planet's past. While these ideas often lack empirical support, they reflect a broader human desire to understand our place in the universe. The collective efforts of scientists, engineers, students, and visionaries continue to unravel the mysteries of Mars. As exploration progresses, each discovery brings us closer to understanding the red planet's history and its potential to harbor life. In 1996, a small rock from Mars ignited a big debate. This rock, known as ALH 84001, was found in Antarctica. Scientists believed it had come from Mars, ejected by an impact and eventually landing on Earth. When examined, it revealed structures that resembled tiny fossils. These structures were shaped like worms and were incredibly small, even smaller than the smallest bacteria known on Earth. Some researchers thought these might be signs of ancient Martian life. They also found magnetite crystals in the rock, which on Earth are often produced by bacteria. This combination of features led to the hypothesis that the meteorite contained evidence of past life on Mars. However, not everyone agreed. Critics argued that the structures could have formed through non-biological processes. They pointed out that similar shapes can result from chemical reactions or mineral growth. Further studies showed that shock waves from impacts could create magnetite crystals without any biological involvement. This weakened the argument that the crystals were definitive proof of life. The debate over ALH 84001 continues. While some scientists see it as compelling evidence of ancient life, others remain skeptical. The structures and minerals in the meteorite are intriguing, but they do not provide conclusive proof. This controversy highlights the challenges in distinguishing biological signatures from geological ones, especially when dealing with samples from other planets. Similar ambiguity surrounds the Viking landers' experiments on Mars in the 1970s. The Viking missions included tests designed to detect life in Martian soil. One such test, the labeled release experiment, yielded positive results suggesting metabolic activity. However, other experiments failed to detect organic molecules, leading to conflicting interpretations. Some scientists proposed that the Viking experiments might have inadvertently destroyed any existing microbes. The tests involved adding water to the soil, which could have been harmful to potential Martian life adapted to dry conditions. This theory suggests that the very methods used to search for life may have eliminated it before detection. The Viking results remain a topic of debate. While the experiments were groundbreaking, their findings are inconclusive. They underscore the difficulty of detecting life on other planets and the need for careful experimental design. Future missions aim to build on these lessons, employing more advanced techniques to search for signs of life on Mars. In 2013, NASA's Curiosity rover detected a sudden spike in methane levels on Mars, 10 times higher than usual. This unexpected finding sparked excitement among scientists, as methane can be a potential indicator of biological activity. However, subsequent observations have shown that methane levels on Mars fluctuate in complex ways. For instance, Curiosity has recorded methane spikes that appear at night and disappear during the day, with seasonal variations and occasional surges up to 40 times the normal levels. These irregularities have led researchers to explore various explanations. One hypothesis suggests that the rover's activities might disturb the Martian soil, releasing trapped methane. Another theory posits that methane could be absorbed in the regolith and released under certain conditions. While these findings are intriguing, they have not provided definitive evidence of life on Mars. The presence of methane alone is insufficient to confirm biological activity, as it can also result from geological processes. In addition to scientific missions, several private initiatives have aimed to explore Mars. For example, the Inspiration Mars Foundation proposed a crewed flyby mission to Mars in 2018. Despite initial enthusiasm, the project faced significant challenges, including technological hurdles and funding issues, ultimately preventing its realization. Similarly, Mars One garnered attention with its plan to establish a permanent human settlement on Mars. The organization relied heavily on media coverage and public interest to fund the mission. However, questions about its feasibility and financial stability led to skepticism, and the project eventually ceased operations. These endeavors highlight the complexities and challenges associated with Mars exploration. While technological advancements have brought us closer to understanding the red planet, definitive answers about the presence of life remain elusive. In recent years, Mars has revealed secrets that deepen our understanding of its potential to harbor life. Discoveries such as subsurface lakes, seasonal gas emissions, and complex organic molecules have painted a picture of a planet that was once, and perhaps still is, habitable. Central to this exploration is the Mars Sample Return Mission, a collaborative effort between NASA and the European Space Agency, aiming to bring Martian soil back to Earth for detailed analysis. In 2018, scientists using radar data from the European Space Agency's Mars Express spacecraft reported the discovery of a large saltwater lake beneath the ice at Mars's South Pole. This finding was later expanded to include 3 additional subsurface lakes, suggesting that liquid water, a key ingredient for life, exists beneath the Martian surface. Adding to the intrigue, NASA's Curiosity rover has detected fluctuations in methane levels within Gale Crater. These methane emissions vary seasonally and sometimes spike to levels 40 times higher than usual. Interestingly, the methane appears at night and disappears during the day, and it isn't accumulating in the atmosphere as expected. Further, Curiosity has identified the largest organic molecules found on Mars to date. These complex carbon-containing compounds suggest that prebiotic chemistry may have advanced further on Mars than previously observed. The Mars Sample Return Mission aims to bring carefully selected Martian samples to Earth for the first time. This ambitious multi-mission campaign is a joint effort by NASA and the European Space Agency. The returned samples are expected to revolutionize our understanding of Mars, our solar system, and prepare for human explorers to the red planet. These discoveries and missions signify a new era in Martian exploration, bringing us closer to answering the age-old question of whether life ever existed on Mars. In recent years, Mars exploration has advanced significantly thanks to technological breakthroughs in artificial intelligence, drone technology, and 3D mapping. These innovations have transformed our approach from merely asking, "Is there life on Mars?" to more strategically considering, "Where should we look next?" AI has become a pivotal tool in Mars missions. For instance, NASA's Perseverance Rover employs AI to autonomously navigate the Martian terrain, analyze rock samples, and identify promising sites for further study. This capability allows the rover to make real-time decisions without waiting for instructions from Earth, significantly enhancing the efficiency of exploration efforts. Drone technology has also played a crucial role. The Ingenuity helicopter, part of the Mars 2020 mission, demonstrated the feasibility of powered flight in Mars's thin atmosphere. Over nearly 3 years, Ingenuity completed 72 flights, providing aerial reconnaissance that informed the rover's path and identified areas of interest. Advancements in 3D mapping have further enhanced our understanding of the Martian landscape. AI-powered terrain mapping enables rovers to generate detailed 3D models of their surroundings, facilitating better navigation and site selection for scientific investigations. These technological developments have shifted the focus of Mars exploration. Instead of broadly searching for signs of life, scientists can now target specific locations with higher potential, such as subsurface lakes or areas with unusual gas emissions. This strategic approach increases the likelihood of significant discoveries and brings us closer to answering the profound question of whether life ever existed on Mars. In recent years, Mars exploration has made significant strides, revealing tantalizing clues about the planet's past and its potential to harbor life. Discoveries such as subsurface lakes, seasonal gas emissions, and complex organic molecules have painted a picture of a planet that was once, and perhaps still is, habitable. Central to this exploration is the Mars Sample Return Mission, a collaborative effort between NASA and the European Space Agency, aiming to bring Martian soil back to Earth for detailed analysis. In 2018, scientists using radar data from the European Space Agency's Mars Express spacecraft reported the discovery of a large saltwater lake beneath the ice at Mars's south pole. This finding was later expanded to include 3 additional subsurface lakes, suggesting that liquid water, a key ingredient for life, exists beneath the Martian surface. These hidden reservoirs could provide habitats for microbial life, shielded from the harsh surface conditions. Adding to the intrigue, NASA's Curiosity rover has detected fluctuations in methane levels within Gale Crater. These methane emissions vary seasonally and sometimes spike to levels 40 times higher than usual. Interestingly, the methane appears at night and disappears during the day, and it isn't accumulating in the atmosphere as expected. While methane can be produced by geological processes on Earth, a significant portion is biological in origin, making this a compelling area of study. Further, Curiosity has identified the largest organic molecules found on Mars to date. These complex carbon-containing compounds suggest that prebiotic chemistry may have advanced further on Mars than previously observed. While not definitive evidence of life, these organics are essential building blocks, indicating that the necessary ingredients for life were present. The Mars Sample Return Mission aims to bring carefully selected Martian samples to Earth for the first time. This ambitious multi-mission campaign is a joint effort by NASA and the European Space Agency. The returned samples are expected to revolutionize our understanding of Mars, our solar system, and prepare for human explorers to the Red Planet. By analyzing these samples with advanced Earth-based laboratories, scientists hope to uncover definitive signs of past life and better understand Mars's geological history. These discoveries and missions signify a new era in Martian exploration, bringing us closer to answering the age-old question of whether life ever existed on Mars. As technology advances and international collaboration strengthen, our ability to explore and understand the Red Planet continues to grow, promising exciting revelations in the years to come. Mars has long been the focal point in our quest to find life beyond Earth. Its proximity and Earth-like features make it an ideal candidate for exploration. However, as we delve deeper into our solar system, other celestial bodies like Europa and Enceladus have emerged as compelling subjects of study. These icy moons, orbiting Jupiter and Saturn respectively, harbor subsurface oceans beneath their frozen crusts, offering environments that could potentially support life. Europa, one of Jupiter's largest moons, is believed to possess a vast ocean beneath its icy surface. This ocean, kept liquid by tidal heating from Jupiter's gravitational pull, may be in contact with the moon's rocky mantle, creating conditions similar to Earth's deep-sea hydrothermal vents, where life thrives without sunlight. The presence of salts and clay-like minerals on Europa's surface suggests a dynamic interaction between the ocean and the seafloor, further hinting at the moon's potential habitability. Enceladus, a smaller moon orbiting Saturn, has captivated scientists with its dramatic geysers that spew water vapor and ice particles into space. These plumes, originating from fractures near the moon's south pole, indicate a subsurface ocean beneath the icy crust. Analysis of the ejected material has revealed the presence of organic compounds, salts, and even molecular hydrogen, a potential energy source for microbial life. The detection of these ingredients suggests that Enceladus possesses the necessary components to support life. Studying these moons alongside Mars broadens our understanding of where and how life might exist in the universe. While Mars offers insights into a planet that may have once been habitable, Europa and Enceladus provide examples of environments where life could exist today. By comparing these worlds, scientists can identify common factors that make a celestial body conducive to life, such as the presence of liquid water, energy sources, and essential chemical compounds. By understanding the conditions that support life on Mars, Europa, and Enceladus, we can better assess the habitability of exoplanets and moons orbiting distant stars. This comparative approach enhances our ability to detect biosignatures and informs the design of future missions aimed at discovering life elsewhere in the cosmos. In essence, Mars, Europa, and Enceladus each offer unique opportunities to explore the potential for life beyond Earth. By studying these worlds in tandem, we not only increase our chances of finding extraterrestrial life, but also gain a deeper understanding of the fundamental processes that make life possible. In our pursuit to uncover life beyond Earth, Mars stands as a beacon of curiosity and potential. The red planet has captivated scientists and dreamers alike, offering hints of past water flows, organic molecules, and conditions that might have once supported life. Yet, to truly understand Mars and its secrets, we must take deliberate steps forward. This journey requires more than just advanced technology. It demands global collaboration, transparent data sharing, and significant investments in life detection methods and contamination prevention. Mars exploration is not the endeavor of a single nation. It is a collective mission that transcends borders and unites the global scientific community. The Mars Sample Return Campaign exemplifies this spirit of cooperation. A joint effort between NASA and the European Space Agency, MSR aims to bring carefully selected Martian samples back to Earth for the first time. This ambitious project involves multiple missions, each contributing a vital piece to the puzzle. By pooling resources, expertise, and technology, international partners can achieve what no single entity could accomplish alone. China's Tianwen-3 mission further underscores the importance of global collaboration. Scheduled for launch around 2028, Tianwen-3 aims to return Mars samples to Earth by 2030. The mission invites international participation, offering opportunities for scientists worldwide to contribute to and benefit from this groundbreaking endeavor. Transparency and accessibility are cornerstones of scientific progress. Open access to data ensures that researchers across the globe can analyze, interpret, and build upon findings, fostering a collaborative environment that accelerates discovery. NASA's Planetary Data System exemplifies this commitment by providing free and open access to data from various missions, including those exploring Mars. Such initiatives democratize information, enabling scientists from diverse backgrounds and institutions to contribute to our understanding of the red planet. Similarly, the European Space Agency maintains an open data policy, allowing researchers worldwide to access and utilize data from its missions. This openness not only promotes transparency, but also encourages cross-institutional and cross-national collaborations, enriching the scientific discourse and leading to more robust conclusions. Detecting signs of life or biosignatures on Mars is a complex challenge that requires sophisticated instruments and methodologies. Investing in the development and deployment of advanced life detection technologies is crucial. For instance, the Mars Organic Molecule Analyzer, set to be part of the Rosalind Franklin rover mission, is designed to identify organic compounds in Martian soil. By analyzing molecular structures, MoMA aims to detect potential biosignatures, providing insights into the possibility of past or present life on Mars. Additionally, instruments like Raman spectrometers play a vital role in identifying mineral phases and organic compounds, offering clues about biological activities. The integration of such technologies into Mars missions enhances our ability to detect and interpret signs of life, bringing us closer to answering the profound question of whether we are alone in the universe. As we search for life on Mars, it is imperative to ensure that our investigations do not compromise the integrity of the Martian environment or the samples we collect. Contamination control measures are essential to prevent Earth microbes from hitching a ride to Mars, which could lead to false positives in life detection experiments. Implementing stringent sterilization protocols for spacecraft and instruments minimizes the risk of forward contamination. Moreover, when returning samples from Mars, we must guard against backward contamination, bringing potential Martian microbes to Earth. Establishing secure containment and analysis facilities, along with rigorous quarantine procedures, ensures that any extraterrestrial materials are handled safely and responsibly. These measures protect both our planet and the scientific validity of our research. Mars has always stirred our imagination, But today, the quest to understand it is no longer limited to scientists in labs. It is a shared journey. Engineers, teachers, students, and everyday people are all part of this mission. Their combined efforts are changing how we explore the red planet. At the heart of this movement is open data. NASA and other space agencies release vast amounts of information from their missions. This data is available to everyone. It includes images, readings, and other findings from Mars. With this access, anyone with curiosity and a computer can contribute. Citizen scientists play a crucial role. They analyze photos, identify patterns, and even spot anomalies that machines might miss. Projects like Zooniverse's Planet 4 invite volunteers to study Martian surface features. Their findings help scientists understand seasonal changes and surface processes. Education is another vital piece. Programs like NASA's STEM engagement aim to inspire the next generation. They provide resources for teachers and students to explore space science. Hands-on activities like building models or simulating missions make learning tangible. These experiences spark interest and build skills. Teachers are the bridge between complex science and young minds. By integrating space topics into their lessons, they make the subject accessible. Students learn not just facts, but also critical thinking and problem solving. These are essential skills for any future explorer. Engineers and scientists continue to develop new tools for exploration, but they also rely on feedback from educators and citizen scientists. This collaboration ensures that missions are designed with broader participation in mind. It creates a feedback loop that benefits all parties. Public outreach programs like those by the Planetary Society further amplify this effort. They create content that educates and engages the public. By making space science relatable, they encourage more people to get involved. What if that shape is a fossil, a remnant of life that once existed on Mars? Or what if it's just a mineral formation, a trick of geology? In 1996, scientists announced they had found possible signs of life in a Martian meteorite named Allen Hills 84001. The discovery sparked excitement and debate. Some saw it as evidence of life beyond Earth. Others urged caution, pointing to non-biological explanations. The controversy highlighted how a single finding could challenge our understanding of life. Now imagine we confirm life once existed on Mars. Even if it's just microbial, the implications are profound. It would mean life isn't unique to Earth. It could exist elsewhere in the universe. This discovery would reshape science, religion, and culture. In science, it would validate the idea that life can emerge in diverse environments. It would prompt new studies into how life begins and survives. Researchers would explore the possibility of life on other planets and moons. The search for extraterrestrial life would gain momentum. Religious perspectives might also shift. Some faiths could see the discovery as part of a divine plan. Others might struggle to reconcile it with their teachings. Overall, it could lead to deeper reflections on humanity's place in the cosmos. Culturally, the confirmation of Martian life would inspire art, literature, and philosophy. It would influence how we see ourselves and our planet. We might feel a greater connection to the universe, or we might feel more isolated, realizing we're not alone. But what if we find no evidence of life on Mars? What if after all our exploration the planet remains silent? This outcome would also be significant. It would suggest that life is rare, perhaps unique to Earth. This realization could make us value our planet more. It could drive efforts to protect and preserve life here. The absence of life on Mars would also raise questions. Why did life emerge on Earth but not on Mars? What conditions are necessary for life to begin? These questions would guide future research and exploration. There's another possibility to consider. Some scientists propose that life on Earth may have originated from Mars. This idea, known as panspermia, suggests that life traveled from Mars to Earth via meteorites. If true, it would mean we're all Martians in a sense. This theory challenges our understanding of life's origins. It suggests that life can spread across planets given the right conditions. The discovery of life on Mars or the confirmation of its absence would have profound effects. It would influence science, religion, culture, and our view of humanity. It would prompt new questions and inspire new explorations. Whether we find life or not, the journey to Mars enriches our understanding of the universe and ourselves. As we continue to explore Mars, we must remain open to all possibilities. Each discovery brings us closer to understanding our place in the cosmos. And perhaps one day, we'll find that we're not alone. Mars has always stirred our imagination. But today, the quest to understand it is no longer limited to scientists and labs. It is a shared journey. Engineers, teachers, students, and everyday people are all part of this mission. Their combined efforts are changing how we explore the red planet. At the heart of this movement is open data. NASA and other space agencies release vast amounts of information from their missions. This data is available to everyone. It includes images, readings, and other findings from Mars. With this access, anyone with curiosity and a computer can contribute. Citizen scientists play a crucial role. They analyze photos, identify patterns, and even spot anomalies that machines might miss. Projects like Zooniverse's Planet 4 invite volunteers to study Martian surface features. Their findings help scientists understand seasonal changes and surface processes. Education is another vital piece. Programs like NASA's STEM engagement aim to inspire the next generation. They provide resources for teachers and students to explore space science. Hands-on activities like building models or simulating missions make learning tangible. These experiences spark interest and build skills. Teachers are the bridge between complex science and young minds. By integrating space topics into their lessons, they make the subject accessible.